So I'm going to talk about arithmetic circuits and some results on how you obtain lower bounds for how you prove lower bounds or how you find hard function for these classes of circuit. So the talk is not meant to be like a full list of all the techniques that exist to prove lower bounds for the circuits that I will introduce. I will mostly cover some work that I've done with Stefan Mengel 2 years ago. So the first step is obviously to describe what I mean by arithmetic circuits and more precisely what I mean by tractable arithmetic circuits. And so that we are all clear about what we are talking about, the arithmetic circuits first. We'll see the tractable one after. So an arithmetic circuit for me is just a computational, graph that look like this, right? So you got a single output, you got a single output gate. Your inputs are labeled by Boolean literals, so which will be 0, 1 variable here. We don't go with -1 + 1, it's 0, 1. And your gates compute operation, so you get the product and the plus operation. And an additional feature is that for your plus gates, their input connectors are weighted by some real numbers, and these can be negative, and this will be important. Good, so it means that some plus gates are actually computing subtraction and not addition. Good, so these objects are, these are models for representing pseudo-Boolean functions, so Boolean input, real number output. And they have been studied under different names, like plus times programs. So arithmetic circuit is the one I'm using. Some product networks, I think you need some other property, but that's, so different names in the literature. For us, this will be arithmetic circuits. And in these talks, all the arithmetic circuits will represent non-negative functions because we want to use them to represent probabilistic circuits, so it makes no sense if they can return negative value. However, even though they represent non-negative functions, they can use negative weight. That's fine. If they don't use negative weight, then we usually call them monotone arithmetic circuits. But it is known that if you allow negative weights, so if you allow subtraction in your circuit, then there are some functions which you can represent very compactly, but in your arithmetic circuits. But as soon as you disable the negative weights, you're only allowing positive ones, then you get exponential size. So since we will want to find lower bounds, exponential lower bounds, it makes sense to target already the most compact class of circuits. So we keep the negative weights as much as possible. Now, an arithmetic circuit, well, if it represents probability distribution, you may want to have a few questions. You may want to answer a few problems and some queries on these circuits, and things like computing marginal probabilities, computing maximum a posteriori. All of this is hard generally, but if you put some properties on your circuits, some restriction on the circuits, then many of these queries can become tractable. And so these circuits, I gather them under the name of tractable arithmetic circuit, which is a very generic term, not precise at all, just to say that these will be circuits that respect a certain combination of properties, which I'm going to describe right now. So the first one is mandatory. It's the decomposability. So it's a property on the product gate. So for convenience, I will assume that all the gates here are binary. And so the decomposability, we've heard about it already. So for all product gates, so a product gate that computes C1 times C2 is decomposable if the C1 and C2 are working on disjoint sets of variables. So here all the product gates are decomposable, so I would call it a decomposable AC. So like this one, the first circuit, it works on X1, X2. The second circuit is working on S3, S4, X5. So that's disjoint. Good, so that's also called syntactical multilinearity. And in fact, it's a syntactical property. If I give you an arithmetic circuit, you can check in polynomial time that it's decomposable. That's not a problem. The second property, on the other hand, is semantical, determinism. And that one is a property on the plus gate. It's saying that whenever I have a plus gate that computes C1 plus C2, or weighted sum. Well, these circuits C1, C2, they have disjoint support. Now, the support of a circuit is a set of truth of assignment of its variables such that the circuit returns a non-zero value. So disjoint support for the two input circuits mean that for every assignment to the variable, one of the two inputs will return zero, at least one. Maybe both of them will, but at least one will. Good. And there are other kind of properties that we can add, like there is smoothness, which I'm not going to describe. We can often take it for granted. The one that is very important for this talk is this one, the structured decomposability. So we've heard about structured decomposable circuits already in this program, but then it has not really been defined, so I'm going to do it here because it's important for me. So it's a kind of restricted decomposability. So with decomposability, your product gates, they are all splitting the variables in some way. Right? You cannot have shared variables between the subcircuits. In structured decomposability, that's also a kind of decomposability, but the separation between the variables, you're not allowed to do all the separation you want. They have to be consistent with some structure which is given to you, and which is a branch decomposition over the circuit variable. So we call it a variable tree or V tree. So just a binary tree like this, whose leaves are in bijection with the circuit variables. Now, I'll say that this circuit is structure decomposable and respect this V tree if I can do the following. If I can color every product gate in my circuit in the following way. So these two product gates I color them blue because they are both splitting x1 from x2, and this is exactly what this node is doing. Good. These two I color orange because they are both separating x3 from x4, which is what this node is doing in the V tree. And the last two, they are both separating x1, x2 from x3, x4, which is what this red node is doing in the V tree. So if I can do this coloring in a way, so if I can do this coloring that is consistent with the V tree, then I say that my arithmetic circuit is structure decomposable and that it respects this V tree. Yeah, so just one slide just to say that so these two things are really, yeah, so some arithmetic circuits, they are decomposable, but they are not structure decomposable. Sometimes you just can't find a V tree. I mean, all function, you can always find an arithmetic circuit which is structure decomposable, but you can also find some that are decomposable but not structured by any V tree. You just have to find two nodes that split your variables in ways so that it would not be possible to find a single V tree that will take into account these two particular splits. So yeah, basically the structure decomposable ACs are a strict subclass of the decomposable AC. That's all. Good. So these are the arithmetic circuits. These are you have some combination of decomposability, determinism. Sometimes you have structure decomposability instead of Bannier decomposability. But that's what I mean by tractable arithmetic circuits. And now, well, since these circuits are very useful to answer a bunch of problems and queries on the function represented, well, obviously, you expect that for some functions, it will be the size of the tractable circuit will be exponentially large. So you expect some lower bounds. You expect some function would be hard for these classes of circuits. And so now I'm going to show how we can find such hard functions. Now, the first technique that you can use is, well, what I call the boring trick, because I don't find it very interesting. But the thing is that I'm actually more familiar with Boolean circuits and with the ones that are tractable, so the ones that respect decomposability, determinism, and so on. And well, it would be convenient if we could just reduce our tractable arithmetic circuits to the tractable Boolean circuits. And of course, we can do this. We just take the plus gate, we replace by OR, we get rid of the weights, the product we replace by AND. And assuming my initial circuit was only using positive weights, Then these arithmetic circuits, after the transformation, I've obtained a Boolean circuit that represents this function. So the indicator for the support of the function. So maybe you have this circuit had no assignment that returned 0 in the first place. So this is just computing the uniform 1 function, but sometimes this will not. And so as you do this, well, decomposability is preserved, determinism too, and you end up in this class of Boolean circuits, which I'm not going to describe, and which are quite well known. We know a lot of hard functions for this. So if you want to find a hard function for your arithmetic circuit, you just take a hard Boolean function, you try to, and you say, okay, that's Boolean, so that's also pseudo-Boolean. I can try to represent it in this way. And because they are hard for the tractable Boolean circuits, they will also be hard for the tractable arithmetic circuits. Now, the problem with this is that, well, you need positive weights, and we don't want this. As soon as you have negative weights here, this operation means that the function that you will get is not the indicator for the support. Yes?
You actually use the weights, even if they're positive. Where do they show up in your trick?
Sorry?
Even when you have weights and they're positive, where do they show up in this translation?
No, they don't show up. We remove them.
Okay, so you don't care about them?
They're basically 1.
Yeah, they become 1. We don't care about them.
So then you compute a different function.
Yeah. This was a pseudo-Boolean function. This was representing a pseudo-Boolean function. And now this represents this Boolean function.
I see. Okay. So it's a different function.
Yeah, it's a different function. But if this one is hard for this class of circuit, then the thing that you were trying to represent in the first place is hard for your arithmetic circuit. But you need the positive weights. And well, you need the positive weights only but not in all settings. Like in particular, if your arithmetic circuit is deterministic, then it's not so hard to prove that you can just always assume that your weights are already positive. Like if I give you an arithmetic circuit and I tell you it's deterministic, okay, then it's computing the same function as this one where I replace the weights by their absolute value. In addition, you can also use determinism if you have both determinism, decomposability, and integer weights. Then not only can you compute Boolean circuits for this function, but you can also compute Boolean circuits for this function. For any constant k, you can compute a lot more tractable Boolean circuits in polynomial time. So you have a lot more candidate Boolean functions which could be hard for your Boolean circuits. Yeah, well, this would generally be intractable without this determinism. But still, we are not satisfied. If you don't have determinism, you still need positive weights, and that's not good. So now I'm going to present another technique, which is a rank technique. And this one does not require positive weights. And this one we'll use to prove lower bounds on the size of structured decomposable arithmetic circuits. You remember, I have my V tree. I want to color my gates. So now we want to prove lower bound for these things. And so the rank technique, the rank technique will use the lower bounds will be the rank of some matrix, which I'm going to define and which I call the value matrix. I think there are other names probably, but I like to call it this way. So I will give an example in a second, but I will just need a partition, a bipartition of my variable, and so I will obtain something like this. So here you have an example function. Never mind what it represents; it's a bit random. And okay, 5 variables, and I decided to partition my variable in the following way: x1, x2, x3 in the first part, x4, x5 in the second part. Now the value matrix for this partition pi and for this function f is defined as follows. So each column is represent an assignment to the variables in the first part of the partition. Each row represents an assignment to the variables in the second part of the partition. And now if I look at a cell in my matrix, then it corresponds to one assignment to the first part, an assignment to the second part, and the content of the cell is just the value of the value of the function at this global assignment to the variable. If your function was Boolean, then you will obtain only a bunch of 1 and 0 in here, and you could call this a communication matrix, or you could just see it as a truth table or a Carnot map or whatever. Yes, just one comment. The order of the rows and of the columns is not important for us. We're gonna take the rank of that thing, and the rank is invariant under permutation of columns and rows. Good, and so the theorem is that, okay, so if you give me a V-tree, so remember that thing, and a partition of the variables that is induced by the V-tree, which I'm going to define in a few seconds, then every structured decomposable arithmetic circuit that respects this V-tree and that represents some function f will contain at least this many gates, the rank of the matrix function for this partition induced by the V-tree. Now, what does it mean for a partition to be induced by a V-tree? Well, it means that I can obtain the partition in the following way. I pick an edge in the V-tree, I removed it, and then I obtain two connected trees, and the variable in the first part will be the first part of the partition. The variable in the second part are the second part of the partition. So in this example, the partition x1, x2, x3 on one side, x4, x5 on the other side is induced by this V-tree. So if I were trying to represent this function as a structured decomposable arithmetic circuits respecting this V-tree, then I would then I know that the rank of this matrix is a lower bound on the number of gates I will need in my circuit. Now, it may not seem very impressive, but remember that you got as many columns as you have truth assignment, as many rows as you got truth assignment on the second part of your partition. So this matrix can be exponentially large, and it is exponentially large. And so you could have exponential rank, and so that's what we want. We want exponential lower bounds. So that's what we are going to. That's where we are going to. Yeah. So in part, a corollary is that if you don't fix the V-tree, you say, okay, I'm representing my function as a structured decomposable arithmetic circuits. I'm not telling you the V-tree, then I can say, okay, no problem. This thing is a lower bound on the number of gates you will need. The minimum over all the possible rank over all possible partitions, but we restrict to the partitions that are balanced. So meaning that you got at least 1/3 of the variable in the first part of the partition and also 1/3 of the variable in the second part. You can always find a balanced partition for any V-tree. Okay, so now our goal is to find the functions for which this thing is exponential in the number of variables. And, well, we found some. So this is an example of hard function. So this function will have some underlying graph, called simple graph, no parallel edge, no directed loop, call it G. And we have this thing. So the vertices corresponds to the variables. And whenever you have an edge, ij, in your graph, then you multiply by 1 plus maximum of the maximum of the two variables. So you cannot further that this thing is never going to take value 0. So if I were to do the boring trick to reduce to a tractable Boolean circuits, I will get a circuit that is uniformly 1. So really not interesting. But it's very good to apply the rank lower bound techniques, because we can prove that if G is an expander graph, so that's a kind of graph that is, I'm not giving the definition, but it's a very well connected graph, and it's very well connected and can have a very small degree. So that's this D equal constant. Then if G is an expander graph, you can prove that this function, for any balanced partition of its variables, then you got this exponential lower bound on the size of the rank. Good. So it means this thing is exponential in the number of variables for these functions for expander graphs. And so since you have infinite classes of expander graphs, which are regular, in fact, then that's it. You find an infinite class of functions that can only be computed by structured decomposable arithmetic circuit of exponential size. And at no point I've never made any assumption on the weights that I needed to use to prove this lower bound. In fact, I can use positive weights, negative weight. Doesn't matter. You will get exponentially many gates in the end. So that's nice. Now, the most interesting part, I think, but also the most complicated, is the proof is the proof of this theorem here. Yeah. So just one word on the proof. So it's the proof uses, you are required first to do some analysis on your circuits to decompose your circuit as a sum of decomposable product, which so if you're familiar with how you obtain circuit lower bound for DNNF circuits in the Boolean world, these things will correspond to combinatorial rectangles, but here I would like to call them arithmetic rectangles, perhaps. And anyway, that's these things, and you prove that these functions have value matrix of rank 1, and then you use that the rank is subadditive, and you obtain your lower bounds, the theorem. So anyway, there is some interesting part which is hidden here. Okay, so now what I wanted to do to finish is to show to give an application of this result. This will be a theoretical application, but still I find it quite interesting. So I'm gonna use this thing to prove a separation between classes of tractable arithmetic circuits. Because you remember I've said that not all decomposable arithmetic circuits are structured decomposable. And in fact, you may wonder as well, perhaps the all decomposable arithmetic circuits, you can make them structured decomposable without increasing the size too much, and so you would have structured decomposability for free. And that's not true. You can prove that you have a separation, so a class of function that will have small decomposable arithmetic circuits, but that will only have exponential size structured decomposable arithmetic circuits. Now, how can we prove this? Well, we need a few things. We need to manipulate a little the arithmetic circuits. In particular, we need to be able to do conditioning. So it's just you have a partial assignments on your variables, and well, you haven't structured decomposable arithmetic circuits. If you assign a bunch of variables, then you obtain then your circuit is still structured decomposable. That's just what we need, yeah, right? If you're structured by a V-tree, assign some variable, you're still structured by the same V-tree. And also an important result is that if you give me two arithmetic circuits that are structured by the same V-tree, then I can obtain another arithmetic circuit that is also structured by the same V-tree, and that represents the product of my two inputs. Now, if you want to take the product by just putting a product gate and putting your two circuits as a children, well, your product gate is not decomposable, so we don't really care about that thing. But if your two input circuits respect the same V-tree, then you have a quadratic time algorithm that will merge them in some way, and you will obtain something that in the end is structured decomposable. And in addition to this, I will need some knowledge about expander graph, and I will need the following thing, which is that, okay, so we're gonna look at the graph over n vertices, and which made in a particular way. So I'm gonna take a fixed path on the vertices first. Okay, so just a straight line, and then so that will be graph G1, and G2 will be just a random path on the vertices. So we got n factorial of them, and you take it uniformly at random. And then you define G1O plus G2 as follows. You take G2, you put it on top of G1, and you get rid of the parallel edges. So the edge that was here, since it's also here, you don't have it in the resulting graph. So that this is not a multi-graph, but really a simple graph. And now I claim, and I'm not going to prove it, but I claim that it's true. Well, I mean, I've done the proof. But that if you choose G2 uniformly at random, then this graph here, it's an expander with high probability. And not only is it an expander, but it's easy to see that all the vertices here, they have degree at most 2 as well. So everyone here has degree at most 4. So that's an expander graph with a small degree. Good. And so, yeah, if you just rewrite the hard function here. I say that fg is the product of, for every edge, 1 plus max. Okay. So I've told you earlier that when G is an expander graph, that function is hard for structured decomposable arithmetic circuit. So with high probability on the choice of G2, that thing admits only exponential size structured decomposable arithmetic circuits. But then you can observe that this function here is actually the product of these two functions here. Well, that's not quite true. Actually, you need a subgraph of G1 because of the parallel edges, so that you need to remove. But for simplicity, you can just assume that this is the case. Okay, so but then what does it mean? If you could represent that thing as a structured decomposable, as a circuit that is structured by some V3T, that thing by the circuit that is structured by the same V3T, well, they have the same V3, so I can take their product in quadratic time, and I will obtain something that is structured and that represents this function. This has to be exponentially large, so one of these has to be exponentially large, at least one. So for all t, either this is big or this is big. One of the two has to be large. Maybe both of them are, but at least one. Okay. However, you could also, if you're allowed to choose different V3s, then you can find a first circuit that represents this one, which is small, another circuit that represents this function, and that is also small. It's possible because they respect different V3s. It's fine. And now you're going to use this to construct your functions, the function to do the separation. Essentially, you're going to use this. So you introduce a fresh variable y, and you just create and you look at this function. Well, I claim that that thing has admits small decomposable arithmetic circuits. That's quite easy to see. You just take a plus gate top, you have a product gate here, and then you put the small circuit for your function fg1, and on the other side, you put the small function for fg2. So this is decomposable. This is decomposable. The whole thing is decomposable. It is a small circuit. It's not structured, and of course it's not structured, because if you were to try to represent that function as a structured decomposable arithmetic circuit, then you have some problem, which is that if you condition your function on y equal 1, you end up with a circuit that is structured that represents this. If you condition it on y equals 0, then you obtain a circuit that is structured by the same V3 and represents this guy. And since the circuit you will obtain by doing this conditioning respects the same V3, you know it has to be large. So that means that your initial circuit that was structured decomposable and representing this thing is exponentially large. And that's it. That gives you the separation. You have a class of functions which are easy to represent as decomposable arithmetic circuits, very hard to represent as structured decomposable arithmetic circuits. And again, I never had to assume anything about weights being positives or negatives. They can be negative. It doesn't matter. The separation will hold. Good. Yeah. So I've been quite fast, actually. Yeah. So that's it. So that's all I wanted to present. So the arithmetic circuits, the obvious reduction to Boolean circuits, which work only in some settings, but you can find some techniques that will work in the settings where you have negative weights. And once you find a result, you can always use it to prove some separation between classes of arithmetic circuits. There are still some separation that that I don't know about. So there are still a lot of open question on tractable arithmetic circuits when you have the negative weights. Otherwise, we sort of know how to analyze them. Good. Thank you.
Are there any questions?
Yeah, thank you for the nice talk. I have a question about the rank theorem where you can prove lower bounds on the rank.
Yep.
Do you need structure there? I mean, can't you prove some kind of similar results if you don't have structure?
Okay, so if I don't have structure, I can go here. So basically, if I don't have structure, I will find a decomposition of my circuit as a sum of rectangles. You mean, you know what are rectangles?
Yeah, I know.
Of these things, but here you will not have the same partition necessarily. I mean, you will have different partition. And then how do you, I mean, here I can just say that I take the matrix of this thing for a given partition, and then just say that so that's.
No, you're right. Okay, no, it was me being stupid. No, sorry.
Yes. No, you're not stupid.
I get
but you get it. That's you will not be able to just say that that this is a sum of your matrix if they do not have the if you have different partition, you may have different dimension of the matrix. And
okay.
The sum is.
Yeah, of course. Yeah, sorry. Thank you.
Yeah. So yes, for decomposability only, we are stuck here. We don't know how to, and we don't know how to prove lower bounds in these settings. This is not the same as combinatorial rectangles.
Yeah, indeed.
Yeah, so regarding this result, which is very, very nice. So the matrix you described to us is essentially a much higher order tensor, but you reduce it to a matrix. Yeah. Have you looked can you derive anything interesting by looking at the entire tensor to examine its rank as opposed to collapsing it down to a matrix?
I'm not very well versed in tensor. Must admit.
Proving lower bounds on tensor rank is much harder than proving this kind of lower bounds.
Yeah,
so I mean, there is a paper by Ranras where he associates the size of arithmetic formulas with tensor ranks, and this is similar techniques that this. I can give you the pointer. Ranras. And basically, I mean, he has some results. The conclusion of the paper is that it is impossible to prove any lower bounds on the tensor rank. So this is your thing. So, but I mean, there are a lot of connections in this direction.
What's the complexity of finding a good upper bound or approximating the rank for a given formula?
The complexity of finding an upper bound?
Yeah. I'm thinking, can we also flip it to have some upper bound, guide the design of a compiler also? If I know the rank is going to be high for this given partition, then why even try?
Well, how would you know that the rank is high? I mean, that's an exponential size matrix. You're not going to compute that thing.
No, but do we have to compute? Is there a way to get an upper bound without having to compute the matrix?
Oh. No, I was going to say you can use the intermediate step. No, I don't know. I have no, I don't know. Maybe. We have not thought about this. Sorry.
Thank you for the talk. Those of us who have been here since August in the program have been exposed to a lot of material about semi-rings. Mm-hmm. So suppose we take the arithmetic circuit and instead of thinking of numbers, we have values from a semi-ring and the plus and the time of the semi-ring. Mm-hmm. That's still a circuit to compute something. what happens to the technique with the rank metrics? Have people looked at such things? And
Well, so,
suppose I get the tropical semiring, so the plus is
Yeah.
mean and the times is plus.
yeah, so okay, so before that, so I forgot to tell it, but the rank technique, it's known already for in communication complexity for Boolean. Anyway, so that's not completely new. But then if you have a summaring, but the thing is that we sort of use here that the rank is subadditive to yeah. We need to express our circuit as this sum here, and since this sum is a sum over real numbers, we can use that the rank is subadditive to say that if we put the rank of a sum of matrix, it's fewer than the sum of the rank of the matrix. But if you change summering, I will assume that this sum will not have the same meaning, and the rank would still have to be subadditive for this new sum for the sum of your summering. See what I mean? Sort of. And so I don't really know how this. I don't know of any other of what the other works have done. Maybe they've managed to do it, but I will not find a way to directly adapt these techniques to any other summering.
Probably a very silly question, but why are you interested in negative weights? I'm, for example, from machine learning, probabilistic reasoning. For us, the weights are probabilities, so are always non-negative. Why?
Why? Because when you have negative weights, you can represent things much more compactly. And so we are trying to find lower bounds for the things that we know are the best to represent. And yeah, so that's the only reason. Like if we could restrict to positive weights, we will have a lot of results, and we have a lot of results for positive weights. But so we are not exploiting the full capabilities of the arithmetic circuits. If you prove something for we prove something we try to prove lower bounds for the strongest possible class. And
so maybe for probabilistic circuits, it would be interesting also to find if you have an equivalent model with negative weights to find an interpretation of these negative numbers.
There's a lot of interest in negative probabilities in quantum information.
Yeah, but these are even more tricky. But maybe also with standard, let's say, real valued probabilities. I don't know.
Questions?
Thanks so much for the talk. I was wondering if you could say a little bit more about how you get the indicator function greater than or equal to k for deterministic and decomposable circuits.
With the k?
Yeah, with the k. Yeah.
Oh, that thing. So we need integer weights. Yeah. Right.
Okay.
Let's see. Well, because, so you want to know when it's deterministic?
Yeah.
So for deterministic, unless I'm mistaken, if you want just suppose you want only the values that are returned by these things, such that you that are greater than some. Okay, we'll say k here. Well, you will just need to find the one that are greater than k in both children, because anyway.
And
if you got greater than k here, since one of them has to be 0 always, so it's
so for the product nodes.
Okay, for the product nodes then.
It's integer weights you can kind of.
So for the product, so that's actually the thing that you cannot do with just without determinism.
Yeah.
For the product node, you just. Oh no! Sorry, I can. Oh no, that was right. Okay, time. Alpha. So here you want greater than say k minus L, and here you want beta, well, perhaps equal L, something like this. And so you need basically you need to create one new node per value between zero and k, and you would obtain something. So that's still this time this product is decomposable because this one was decomposable. You will get that this is deterministic if because all the this one. So if you got another one here for beta and you only take the assignment that's return value L prime, well, you cannot. Well, does it work? Yeah, yes, I think it does. Yeah. Beta cannot return both L and L prime at the same time. So this, if this is not zero, this will be zero. So one of the two will be zero. And you have a lot of children, as many as you have L's between 0 and k. So you will need to create a k copy of every node in your original circuit. So if k is constant, which I'm assuming, because if k is not constant, I can prove it's not possible. Then it's fine. You got a polynomial time transformation.
Yeah, that makes sense. Thank you. Did you have a question? No. Anybody have a question? Okay.
So I actually have a stupid question. So at some point you showed that for deterministic circuits, you can just take like the absolute values of the weights,
Yes.
but I didn't get, like, are you saying they will have the same value, or that you can build a circuit with the...
I'm saying that if your circuit has a minus, as a negative weight, you can remove the minus. And that's the same circuit. That's the same function. No, sorry. That's the same function that is computed by a circuit of the same size.
So I don't get it. Like if I have one node, just one node, one plus node with just one minus value of a weight.
The circuit is computing a non-negative function. That's
okay, right.
So I said it in the beginning, but I should have stressed it at that point. Yes, that's why it works.
Okay.
Otherwise, it's not. Otherwise, I don't know. Otherwise, it would be hard to remove the negative weights, I guess. But yes, because they are computing non-negative function, because we want them to represent probabilistic distribution, potentially not normalized, but then non-negative function, so we can remove the negative weights. That's the reason.
Okay. No more questions? Okay, so let's thank the speaker again. Okay, so that was the last talk of today. The idea is that we now will have a